should I just plan to start myself when the hour starts, or will there be an introduction?
I think we can give an introduction so we can have like a cue when to start recording. So
okay, terrific.
Let me just.
Yes, I will give like a very short introduction and then we can start.
Okay, so there's no one else waiting right now. So if you wanted to, we could give it a go.
Minutes. Yeah, so we can wait. See.
Yeah, one more minute. Yes. Okay.
Good afternoon.
Hello, everyone. We're ready to start the second session of this course number 4, Foundation of Model Theory, with Professor Sater Wassaf. So we can start. Go ahead.
Very good. Thank you all very much for coming. I'm glad to be doing the second part of the class today. I want to start with a, oops, I do want to start. There we go. With just a reminder of, so the 2 take-home points that I wanted to make last time were that the ideas behind rings and modules have many applications, and particularly modules, the topic of this course. They give a unified way to study vector spaces and abelian groups, but also other constructions. And then the points for today will be that they're really, depending on how you count, there are 2 of them or 4 of them, but I like to think about ring theory and module theory as, if you want to understand a ring, you should understand its modules. And I make the point that this is like the CILO theorems, but for rings. That if you want to understand a group and prove the CILO theorems, for instance, that you want to understand the sets that the group acts on. You want to understand the group actions for that group, and that's what allows you to prove the structural results from the numerical information about your finite group. And another way to think about this that's sometimes helpful, if it gives you any perspective, is that this is essentially representation theory for rings. And that's in a very concrete sense, in the sense that representations of groups are just modules over the group ring. And we're not going to talk about that explicitly. The main theme today is this take-home point number 4, which I hope to enforce to you on several occasions, is that elementary rings have only elementary modules. So if I want to understand a ring by understanding its modules, how can I do that? Well, if I have an elementary ring, then I can understand its modules because the modules are all elementary. And conversely, if the modules are all elementary, and that tells me that my ring is elementary, then by understanding the modules, I've understood the ring. Okay, and this is an incredibly powerful technique. In some ways, it's really the main reason to focus on rings and modules. And I hope to convince you of that today and a little bit tomorrow. So we have 4 items in our outline for today. The first one will be very short. It's called niceness. What does it mean for a ring to be nice and how do I think about niceness. And so we begin with an assumption that we'll carry for the entire lecture today. The math R will always stand for a non-zero commutative ring with identity, and the math BB K will always denote a field. And the idea, which you'll see a little bit of, is that in general, modules can be complicated, not of a nice particular form. And I'll remind you, for instance, of the form that we had earlier in the week, the fundamental theorem of finitely generated modules over a principal ideal domain. But in general, if you give me an arbitrary ring, then the modules will be complicated. And so a question that motivates this entire area and my take-home point number 4 is, when are all R modules nice? And we'll see various versions of what it means to be nice as we move through the lectures. And the correct but not necessarily helpful answer here is that the modules are all nice over a fixed ring if that ring happens to be particularly nice. And so we will start to talk about what I mean by niceness by talking about free modules. And I know that some of this is review from the previous course number 2, but just to make sure that we are all on the same page, I start with a module over my non-zero commutative ring with identity, and I look at a subset of that module, not necessarily a submodule, but that subset is what I call a basis if every element of the module can be written uniquely as a finite linear combination of elements from the basis. And so there are two conditions that are built in there. There's an existence condition and a uniqueness condition. The existence of linear combinations is a spanning condition if you're thinking in terms of linear algebra. So every element of my module can be written as a finite linear combination of basis vectors where the coefficients come from the ring R. So that's the existence condition for the basis definition. And then the uniqueness, that these can be written uniquely as finite linear combinations, is a linear independence condition. And so what I mean by that, I'll state the most general version here, that if you give me two representations of the same element, say with possibly different coefficients in principle, then this set B is linearly independent if the only way that can happen is, in fact, for the coefficients to all be equal. So a basis in this case is just like a basis in the vector space linear algebra situation, that I'm looking for a span condition and a linear independence condition. Now, not every module will have a basis. This is, in fact, one of the things that makes certain modules very nice. So we specify that a module M is free if it has a basis. And some examples of those. So if I look at R to the N, that's the notation that I use for the set of all column vectors of size N, where the entries come from the ring R, then that module where the scalar multiplication, how do I multiply an element of the ring times a column vector? Well, you do it just like in linear algebra class. You multiply all the entries. So that's an R module, and it is free with basis given by the standard basis. So the basis vectors are, if you like, the columns of the identity matrix. So E1 has a 1, 0, 0, and so on. E2, 0, 1, 0, and so on. until we get to En, which has a 1, right? So the entries are given in terms, if you like, of the Kronecker delta function. So this is E1, E2, and En. And one can characterize these particular free modules. So a module has a basis with exactly n many elements if and only if it's isomorphic to the one that we have from the previous item in the example list, that it's one of these sets of column vectors. Okay. And for me, I want to reiterate, isomorphism, not in a, right, is an abstract concept, but I really think of that as saying that M is essentially the same, that algebraically, I cannot really tell the difference between M and R to the N. Examples of non-free modules. So if you give me an integer N that's greater than or equal to 2, and consider the quotient Z module or abelian group, then that is not a free Z module. And the essential point here is that if I take the integer N times the element, any element in there, then I get the 0 element. And so there are no elements of Z mod N that are linearly independent over Z, right? And so when you start looking at your basis condition, you can't even start the linear independence condition. There are literally no elements in there that satisfy that. And similarly, if I take any non-zero commutative ring and mod out by an ideal that's not the entire ring and is not 0, then in fact, the same argument shows that this is not free over R. And notice that I had to rule out 2 degenerate cases. If I equals R, then this quotient is 0, which is free. And if I equals 0, then this quotient is isomorphic to R, which is also free. So there are 2, the trivial ideals will give you a free module, but as long as you have an ideal that's not trivial, then you will have a non-free module. And we'll see in a minute that this is the key to understanding the niceness condition in terms of free modules. Right. So before I can do that, I want to talk about finitely generated modules. And I know that this was talked about before, but we'll go ahead and hit it again. So a subset of my R module is said to be a generating set if every element can be written as a finite linear combination of elements from the set B with coefficients coming from the ring R. Notice the difference between this and the basis condition is that I'm saying the existence of a representation. So I'm assuming the spanning condition, but I'm not assuming the uniqueness. So I'm not assuming the linear independence. And we say that M is finitely generated if there exists a finite set B that gives me a generating set. And while I usually say that it has a finite generating sequence, that it can be generated by a list of elements, a finite list of elements. Some examples of generating sets. So if you have a basis for your module, so if you have a free module, then every element can be written uniquely as a linear combination of those elements. In particular, every element can be written as a linear combination, and so every basis is also a generating set. But the converse fails in general, and I'll show an example of why that's true in just a second. In particular, since Rn has a finite basis, those basis vectors E1 up to En, it has a finite basis, which means it has a finite generating sequence, which implies by definition that it is finitely generated. And we will see that in some sense, this is the prototype, or at least the model, for all the finitely generated modules. And it's either a good or a bad model, depending on the way things work out. If I'm in the situation looking at the module R mod I, that one is generated as a module by a single element, namely the equivalence class of 1. In particular, it has a generating set consisting of one element so that it's finitely generated. Notice that by what we said on the previous slide, this module does not have a basis. So this is an example showing that I can have a generating set without having a basis. Okay, so strong failure of the converse from part 1 here. Now, I said that this one has a generating sequence. It has a finite generating sequence, but it is in fact true that every module has a generating set. And I'm not going to write out the proof of this, but the point is that once you allow for infinite generating sets, then you can just use the entire module itself as the generating sequence, the generating set over itself, because every element of M can be written as a finite linear combination of elements of M just by taking coefficient 1 in front of the element and zeros everywhere else. And then one can use that along with an exercise that we'll look at the end of the lecture today to show that even if your module M does not have a basis, I can find a free module, so a module with a basis, and an R module surjection, so that's onto map from my free module into my regular module. Right. So I said that the free modules are the prototypes or the models for all of the finitely generated modules. So let's see what I mean by that. So here's a proposition: for every R module M, the following conditions are equivalent. First, my module is finitely generated. Second, there exists an R module epimorphism, not from an arbitrary free module, but from one of these finitely generated free modules. So I have a model for my module M that's not just a free module, but a free module with a finite basis. And in terms of quotient modules, that is equivalent to there existing an N and a submodule of R to the N, such that the module that I started with is isomorphic to R to the N mod K. And as with many ideas in the area of abstract algebra and module theory, this may feel esoteric, but it is the key to opening the door to much of the study of modules, including the gateway to homological algebra, which we'll see a little bit of in the lecture tomorrow. Now I want to sketch, we've got most of the tools for proof of this result. So let's go through that. First of all, we'll prove that 1 implies 2. So assume that the module is finitely generated, and we will construct an R module epimorphism from R to the N to M. And the way that we will do it is start with your finite generating sequence with n elements in it, and the number of generators that we use here will be exactly the size of the free module that we use for our epimorphism. So once you've given the generating sequence, we will build this map from R to the N to M. So what's it going to do? The elements in R to the N are the finite linear combinations of the basis vectors. And what we're going to do is we are going to take this linear combination of basis vectors and map it to this linear combination of the generating set, generating elements. And if you like, what we're really doing is we're saying each EI basis vector should get mapped to each XI generating set, and then extending that assignment to an actual R module homomorphism. Now, one has to prove a whole bunch of things that I'm going to skip over and leave a little bit of it to the exercises. So the first thing one has to prove is one has to prove that that's a well-defined function. And we're going to do that in the exercises. That has to do with both the spanning and the linear independence condition. So the spanning condition tells me that every element of the domain has this form. The linear independence condition tells me that this representation of my element of the domain is unique. And that's the key to being able to show that this is a well-defined function. And once you do that, just like what we saw in the class yesterday, once you show well-definedness, then it's actually fairly straightforward to show that it's an R module. And of course, I've misspelled the word epimorphism, so I'll fix that hopefully in the final version of the notes. Why is it an epimorphism? Well, the generating sequence condition. So what do I need to show in order to show epimorphism? I need to show that every element of M is an image of something from the domain here. And so the generating sequence condition tells me that every element can be written in this form. And by definition of this homomorphism, an element of this form can be written in the image of the homomorphism. So that's why once you have that it's a well-defined homomorphism, the epimorphism condition is automatic because of the generating sequence assumption. And we'll see in the exercise that in order to get a well-defined homomorphism, one only needs to have chosen some elements of the module. They don't have to be a generating sequence. So that explains why 1 implies 2. And really, I want to think about this in terms of if I have a finitely generated module, then it can be modeled by a finitely generated free module. What about the converse? So if I assume that there's an R module epimorphism tau from R to the N to M, I need to show that my module M is finitely generated. And the way that you do that is essentially by following the original argument. You show that when you apply tau to the given basis vectors for R to the N, then that in fact forms a generating sequence for M. And let's see here, let me write a couple of symbols here. So my M can be written as tau of X because of the surjection condition, and my X can be written as a finite linear combination of Ri EIs, which I can write as sum over I Ri times tau of EI. And so this shows that an arbitrary element of my module can be written as a linear combination of this finite list. And that's exactly what it means for this list to be a generating sequence. Good. What about condition 3? So the implication 2 implies 3, I want to highlight that is an immediate application of the first isomorphism theorem. So the first isomorphism theorem says that if I have an R module epimorphism, then the target can be written as isomorphic to the domain mod the kernel. And so that K that I want to use for my submodule in condition 3 is precisely my kernel. And again, this is why I'm using the letter K for my submodules, because I really am thinking about them as all kernels of something. What about the converse to that one? Well, if you give me an isomorphism from R to the N mod K to my module M, I can take the natural surjection from R to the N onto the quotient. That gives me, in the composition, an epimorphism from R to the N to M, which is exactly what I wanted. And we will talk extensively about how good of a model Rn is for a given module M today and tomorrow. Cool. So remember the slogan that I said, that the take-home point, that all modules are elementary if and only if your ring is elementary. And this theorem, which is very, very classical, is the first example of that. So it says that for your ring R, the following conditions are equivalent, that every module is free if and only if R is a field. So that's sort of full stop. All the modules are nice if and only if the ring is nice. Right? So answering in some sense the question that I posed at the beginning of the lecture today, when are all the modules nice? If you believe that these modules are nice, then you'd better believe that these rings are nice, and I do. And one of the points of part 2, so if you think about this logically, condition 1 is much stronger than condition 2, but the idea is that if you assume that R is a field, then you get to conclude this very strong condition. But if you want to check that R is a field, you only have to check this weaker condition, that you only have to check the finitely generated modules. And that, I'll just tell you, is a very, very handy thing to be able to do. If you just want to, if you have a condition that only needs to be checked for finitely generated modules, that makes life a lot nicer and a lot simpler. I'm going to sketch the proof of this result as well. So as I mentioned, if every module is free, then every finitely generated module is free. I don't like to use the word trivial in general, but that is a trivial logical consequence. What about 2 implies 3? Now here is where we're going to use the example that we saw previously. If I want to assume that every finitely generated module is free and conclude that my ring is a field, I will instead argue by contrapositive, or if you like, by contradiction. Let's assume that R is not a field and show how to construct a finitely generated module that's not free. So assume that R is not a field. Now I'm going to use a condition that is true for fields that we didn't talk about before. And it's exactly this, that a ring is a field if and only if there exists a non-trivial ideal. And this is tied together with the idea that in a field, every element is a unit, every non-zero element, and so every non-zero element generates the entire ring as an ideal. And so if you're not in a field, you have a non-unit, and so you can generate a proper non-trivial ideal. But once you have that non-trivial ideal, then the previous example that we had said that here is a module that's not free, right? And in fact, I should have pointed this out in here, this module we talked about is generated by a single element. So in particular, it's finitely generated. So we've established that if this condition fails, then this condition fails. So 2 implies 3 by contrapositive. What's next? We'll prove 3 implies 2. And you'll notice I'm not using the most efficient logical proof method for these proofs. That's actually intentional. These proofs are actually easier to do this way. Well, yeah, I'll say something about just a second. So the implication 3 implies 2 is a standard result from linear algebra that you show if you assume that you're working over a field. So your modules are the same thing as vector spaces. So every finite spanning set can be pruned or reduced to a linearly independent spanning set by removing linearly dependent vectors one at a time from the spanning set. And so that shows you that your finite generating sequence can always be transformed into a basis. So that says every finitely generated module has a basis. Now, in general, at least in the linear algebra classes that I've seen, one only talks about basis vectors in the finite dimensional case. There is a version of this argument for vector spaces that are not necessarily finite dimensional. It uses some technology that I'm not going to have time for. At least the proof that I know of uses Zorn's lemma, right, which is equivalent to the axiom of choice, and there's a little bit of a machine. So up here, right, this is really an outline of a proof. I've shown you the pieces that we have the technology to understand. And now I think we come to a reiteration of our take-home point. Elementary rings have only elementary modules, and conversely, every module is nice if and only if your ring is nice, right? So with respect to the niceness condition of being a field, that here is the corresponding niceness condition for your modules. And I want to reiterate, this might be viewed as a silly example because most modules over most rings are not free. It really is the gateway idea to much of the important work in homological commutative algebra. Cool. So that's what I wanted to say about free modules in particular. These will come up over and over again in the later bits of the lectures, but now we will move on to 3 topics about submodules. And we'll get a little history today, a little bit later. Right, so first, I'll remind you of something I know that you saw in course number 2, in the preschool is the notion of a principal ideal domain. And I will not use the abbreviation PID because I realize that in Spanish, the letters are rearranged. And so I will spell out principal ideal domain in all of these notes. So what is a principal ideal domain? So if we break the term into pieces, it should have to do with principal ideals, and it should have to do with domains. And so a principal ideal domain is, first of all, an integral domain, and it is an integral domain such that every ideal is principal. And what do I mean by that? I mean that every ideal is not only generated by a finite list of elements, but can be generated by a single element. And hopefully you've seen these topics before, that the ring of integers and the polynomial ring in one variable over a field, those are two examples of principal ideal domains. And then hopefully your two favorite examples of rings that are not principal ideal domains are polynomial ring in one variable with coefficients into integers, or polynomials in two variables over a field. And just to be clear, in the first case, the classical example of an ideal that is not principal is the ideal that is generated by 2 comma x. And in the second case, you use the ideal generated by x comma y. So in each case, those ideals are given to you in terms of a small generating sequence, and one has to give an argument in order to explain why you cannot find a shorter generating sequence. But it is a fact, and so here are two examples of ideals that are not principal, and so these two rings are not principal ideal domains. So here is the condition of niceness that corresponds to, if I were to say that a ring being nice means that it is a principal ideal domain, and you can agree that these are pretty nice rings, hopefully. That is equivalent to every submodule of the ring being free, right? So just like we had in the niceness condition for a field, all the modules are free. Here, I'm not saying that all the modules are free, but some particular modules are free, that all the submodules. Right? And remember that the submodules of R are just the ideals. So I'm asking that those are free. And that is equivalent to every submodule of every free R module being free. And that is equivalent to every submodule of every finitely generated free module is free. And so you should think about this as a parallel to the result about fields, that the ring is nice if something about free modules, if and only if something about finitely generated free modules. And we're not assuming that all finitely generated modules are free, but every submodule of every finitely generated free module is free. Okay. So slightly different. And hopefully when you saw the proof of the fundamental theorem for finitely generated modules over a PID, you saw some inklings of this when you did the Smith normal form and finding those divisors that you can diagonalize for your matrix. So let's come back to the take-home point. Here are two of the conditions that we had from the previous slide, that my ring is a principal ideal domain if and only if every submodule of a free module is free. So this is saying that my ring is nice if and only if there's a niceness condition for some modules. And from the results that you saw in course number 2 earlier in the week, that if you have a principal ideal domain, then it is an integral domain such that every finitely generated module is a direct sum of cyclic modules. And in fact, this condition is equivalent to being a principal ideal domain. And for the experts in the room, I'm thinking about a field as a special case, a degenerate case of a principal ideal domain, because it is an integral domain where every ideal is principal. And so from our take-home points, your elementary ring, your principal ideal domain, which most rings are not principal ideal domains, just like most rings are not fields. So your elementary ring only has elementary modules, and if your ring only has elementary modules, then it has to be elementary. So here is another instance of an important condition for rings that is understood in terms of conditions on the modules. And so it also hits this take-home point that if you want to understand your ring, you can do that by understanding its modules. Would I like to prove that my ring is a principal ideal domain? Well, one way that I could do that is by showing that every submodule of a free R module is free. And while that seems like an extreme thing to do, it is something that is done sometimes in practice. And we've been light on a little bit of examples. So here's one in the example that I had previously of a principal ideal domain, an integral domain that's not a principal ideal domain, right? Here's the ideal that we said was not principal, and it fits in with condition 3 as well, because it is finitely generated. It's generated by 2 elements, but it is not a direct sum of cyclic modules. That takes a little bit of work to show, but it can be done. So that shows for this example where condition 1 fails, condition 3 also fails. As well, condition 2 fails because here is a submodule of a free module that is not free. And again, as with proving that it's not a direct sum of cyclic modules, it does take a little bit of work to show that it's not free. Now, if you are less geometrically inclined and more arithmetically inclined, you can get the exact same information from this example of my non-principal ideal domain. And the thing that you might want to notice from this is that these examples are not pathological ones, because this is still a particularly nice ring. It's a unique factorization domain. So is this one. And so we're not having to look at very exotic examples of rings, not like the ones we'll look at in the exercises, in order to find situations where one can understand the failure of these conditions. Okay, what's next? Oh yeah, that's good. Yes, so now we are going to give a corollary to this fact. So this is just a repetition of 2 of the pieces from that theorem that we talked about before, and I want to use those to obtain the following corollary. So the corollary says that if you have a principal ideal domain, then every submodule of R to the n is in fact finitely generated. And this is a true corollary of the fact because if I assume that my ring is a principal ideal domain, take an arbitrary submodule of R to the n, call it K, then in fact, it's isomorphic to R to the K. So it's not only finitely generated, it's free, but in particular, it is finitely generated. And in fact, one can get, I jumped ahead of myself. One can ask the question of, well, if this condition is extremely restrictive, right, it only happens when you're a principal ideal domain, can this slightly weaker condition be used to identify some other nice classes of rings, another niceness condition? And one thing that's worth noting is that if this condition is satisfied, so if every submodule of every finitely generated free module is finitely generated, then in particular, when n equals 1, that says that every submodule of R is finitely generated. And remember that the submodules of R are just the ideals of R. And so if the conclusion of the corollary is satisfied, then in particular, every ideal of the ring has to be finitely generated. And that actually ends up being a very special condition. So I want to talk about what that condition looks like, and then we'll give it a name. What does it look like is encapsulated in this theorem. So if I know that if every submodule of every R to the n is finitely generated, we said that that implies that every ideal is finitely generated, right? But what this theorem says is it says that the converse is true as well, that these two conditions are actually equivalent. And they imply an even stronger condition that every submodule of every finitely generated R module is in fact finitely generated. So this condition is saying that every submodule of this particular finitely generated module is finitely generated. This condition is saying that every submodule of this particular finitely generated module is finitely generated. And the condition 3 is saying that once you have either condition 1 or 2, then in fact, you get this much seemingly stronger condition that every submodule of every finitely generated module is finitely generated. And let me stray from the notes for just a second to make a point. I'm talking about this finite generation condition over and over again. Why is that a valuable thing to do? Well, our brains can really only hold finite amounts of data at a given time. And so if you want to understand a particular mathematical object, it is extremely helpful to be able to understand that object in terms of a finite list of data, right? And so the finitely generated modules are the ones that in some senses we have a chance of hoping to understand in general. For instance, if you want a computer to represent these modules, then you mostly generally want some sort of a finiteness condition like this, so that your finite computer and its finite data storage can actually keep track of a set that's not necessarily finite, right? And that's a very powerful thing to be able to do. Now I am going to give some pieces of the proof of this. So the proof of 3 implies 1. So this one is almost trivial because, as I said, here is a finitely generated module. So if I know that every submodule of every finitely generated module is finitely generated, then in particular, every submodule of this finitely generated module is finitely generated, and therefore every ideal of the ring is finitely generated. 1 implies 2 is where I'm going to sweep some details under the rug. If I know that every submodule of R is finitely generated, then I can use an induction argument on N to conclude that every submodule of R to the N is finitely generated for every N. And I want to be specific here. One has to be careful with this induction argument. There are some false proofs of this result that are very easy to overlook. And so one has to be careful in one's induction argument. I'm not going to focus on that here. I'm going to focus on the 2 implies 3 result because it has to do with the modeling that we've done with our modules using finitely generated free modules. And so let's assume that condition 2 is satisfied. So I want to assume that every submodule of every finitely generated free module is finitely generated. And I want to prove that every submodule of every finitely generated module is finitely generated. So we'll let M be some finitely generated module, and we'll let K be a submodule. And I need to show that that submodule is finitely generated. And we'll see in the exercises an example of a situation where this fails, where you give me a very nice finitely generated module and a very reasonable submodule that's not finitely generated. So this is not a capricious thing to do at all. So how am I going to show that K is finitely generated? Well, I'm going to use my model. So M being finitely generated says that I can find an epimorphism tau from a finitely generated free module to M. And now I can understand my submodule K by looking at its inverse image inside of R to the N. And remember, just like yesterday when I talked about the kernel, I'm not suggesting that tau is an invertible map. This is the set of all pre-images of all the elements of K under tau. Now, since K is a submodule of M, it's a fairly standard thing to show that the pre-image of K is a submodule of the domain R to the N. But now I have assumed that every submodule of R to the N, is finitely generated. And so this module is finitely generated. Now, so tau inverse of K is finitely generated. And the fact that tau is surjective tells me that I can recover the entire module K by applying tau to the submodule T in tau inverse of K. So I start with, let's draw this. So R to the N maps to M by tau. I have here my submodule K, map is tau. I look at its inverse image, tau inverse of K here. Submodule of R to the N is finitely generated. And then I apply tau. In general, that'll just give me tau of tau inverse of K, which will be a submodule of K, but the epimorphism condition guarantees that those two are equal. And then it follows that since this module is finitely generated, any homomorphic image of it is finitely generated as well. And so K has to be finitely generated. So what do? We used, in order to prove that every submodule of my finitely generated module is finitely generated, I translated this submodule to a submodule of my model. right? R to the n I'm thinking of as a model of my module M. I took the submodule here, translated it to a submodule here, used the assumption about R to the n, and then pushed that information back down to the module M, using very specifically the fact that I have an epimorphism. Good. Now, I'm going to be frank and honest with you. The rings that satisfy these conditions are some of my favorite rings in the whole world. And they have names. So the rings that satisfy the equivalent conditions of this theorem are called Noetherian rings. And I'm going to give you some examples of those in a second, and then a little bit of history. So first example, every field is Noetherian, and we can see this in one of two ways, or there are several ways to see this. You can see this because every ideal inside a field is trivial. And that tells me that I is either generated by 0 or I is generated by 1. So in the case of a field, every ideal is very finitely generated, right? These are principal ideal domains. So all the ideals are principal. Alternatively, if you want to think about it, then you can think about it in terms of this condition that says, so if I have K is a field and I have a submodule V of K to the N, well, that is a subspace of K to the N. And we know from basic linear algebra that V has to have a basis, V1 up to Vm, such that M is less than or equal to N. In particular, it has a finite basis, so it is finitely generated. And so standard linear algebra results translate to say that every field satisfies this condition. And once you know that every module over a field has a basis, then you can use this condition as well. Okay. So that's your first example. And let's go back to the word nice that we talked about at the beginning. These rings are incredibly nice. I claim that these rings are also quite nice, although they are not so restrictive that they can't be useful. So for instance, the rings that occur in number theory and in algebraic geometry are all Noetherian, we'll see in a minute, but they are not fields. So this niceness condition is flexible enough to allow for it to include the rings from number theory and algebraic geometry, and from combinatorics and graph theory, the rings that I was talking about previously. Another example, using similar reasons, that every principal ideal domain is in fact Noetherian, and you could get that from this condition by definition, because principal ideal domain says that every ideal is principal, so every ideal is generated by a single element, which is very finitely generated, and so those rings are also Noetherian. And this sort of lends some credibility to what we talked about before, that over a principal ideal domain, every submodule of every finitely generated free module is in fact finitely generated. Cool. Now, there are two more examples And I want to see how much time I have. I think I'll have time to do this, but we'll wait until the end. That the property of being Noetherian is respected by when you mod out by an ideal. So if you start with an Noetherian ring and you take any ideal of your ring and mod out by it, then the corresponding ring is Noetherian. And that's absolutely essential in the algebraic geometry examples and the combinatorics examples, as we'll see in just a second. Before we talk about that, let us talk about the name Noetherian. Today is full of a lot of favorites for me. One of my favorite mathematicians, possibly my favorite mathematician ever in the entire history of the world, is Emmy Noether. She lived a somewhat short life, the early 19th century, late 19th century to the early 20th century, and she's one of the most influential mathematicians of the 20th century. And not only influential, but influential in spite of the fact that she faced incredible obstacles to even completing her PhD degree in mathematics. To go through the things that she went through, and I encourage you to look at the Wikipedia page for Emmy Noether. You can read some of the things that she overcame in order to achieve the things that she did, but to sort of stress how much of a landmark mathematician she was. Not only was her work fundamental in abstract algebra, but in her early career, what's called Noether's theorem is fundamental. They call it one of the most, if not the most important theorem ever proved for modern physics. Okay, she was the one who recognized that homology groups are giving you information about things like Euler characteristics for graphs, that these things that you are getting by counting edges and vertices, you can see those by using vector spaces or modules or abelian groups. This whole notion of ideals that I've been talking about so much in commutative rings, she was the one who turned that into a thing. She didn't define the notion initially, but she was the one who recognized that it was the key to understanding so much in algebra, and therefore so much in geometry, combinatorics, analysis, topology. And this is one of the examples of this quote that she's credited with several lines of research published by other mathematicians in fields that were far removed from her main work. So for instance, she only wrote a small number of papers about ideals in abstract algebra, but I believe it was van der Waarden, who was a student of hers or a mentee of hers, who wrote a famous algebra book that really, really made the idea of ideals a big thing. And those were all based on lecture notes from courses that she taught. Right. So this famous book by another mathematician, van der Waarden, really, really was her work. And she was incredibly generous with her ideas. And I think that it's very important for us to remember who she was and all the things that she gave to the mathematical community. Okay. So I gave you 3 examples on the earlier slide of Noetherian rings. I gave you a field, principal, ideal domain, and then quotient of a Noetherian ring. The 4th important example is another item that has a name attached to it that we'll talk about in a second. So it's Hilbert's basis theorem, which says that if the ring R is Noetherian and you consider the polynomial ring with coefficients in your ring R with one variable, then that new ring, although it is in some senses much larger than your original ring, is also Noetherian. And this is the key for when you put it together with the quotient result on the previous slide of understanding all of those examples that I mentioned on the first day. So here are the corollaries to Hilbert's basis theorem, that this tells you what happens if you join a single polynomial variable, but the same thing is true if you do this with a finite number of variables. So if R is Noetherian, then so is any polynomial ring over R infinitely many variables, and so is any quotient of any polynomial ring infinitely many variables. Because if I know that this ring is Noetherian, then the example on the previous slide shows that every quotient is also Noetherian. Now remember that that implies, right, so I'm assuming that every ideal of R is finitely generated, and concluding that every ideal of this much larger ring is finitely generated. In particular, those ideals that we looked at in algebraic geometry, right? So if you take your subset of k to the d, where k is a field, and you look at the set of all polynomials that vanish at all the points of your set V, that is an ideal in this ring, which is Noetherian, right? Because we said, for example, that every field is Noetherian on the previous slide. So by the corollary to Hilbert basis theorem, every finite polynomial ring with coefficients in a field is also Noetherian. So every ideal in this ring is finitely generated. In particular, this one is. And that's absolutely fundamentally crucial. The algebraic geometers, they could do very, very little work without this absolutely fundamental fact. And so that was Hilbert's basis theorem. You probably knew Hilbert's name today, but just in case, we'll say a little bit about him. He was also born in the late 19th century and died in the early 20th century. He lived much longer than Emmy Noether did. He is called by many folks one of the last, if not the last, universal mathematicians. At the ICM, the International Congress of Mathematics, was one of the very last ones in the 1800s. He posed a list of 23 problems, and these problems were in extremely different areas of mathematics. They were in logic, number theory, algebra, and these fields like abstract algebra, algebraic topology, computation theory, all of those were developed in large part because of these 23 homework problems that he gave to the people at that very important conference. And they did, I think there's still some of these questions that are open. Most of them have been resolved. Some of them were proved and some of them were disproved, but they still do fuel lots and lots of the research that we see even into the 21st century. And just like with Emmy Noether, we have 3 pictures here of David Hilbert, a youngish one, a middle-aged one, and maybe an older one. All right. So we got through the same number of slides today, a little bit faster than on the previous day, which is fine. Let me bring us to our conclusion. And then what I'll do is I'll go back, and that result that I said that if I had time to prove, I would prove, I will prove. So first of all, in our conclusion, right, we had 4 take-home points. The first one, that you want to understand a ring by understanding its modules. And we've seen several instances of this, right? If you want to understand the fields, those are exactly the rings for which all the modules are free. If you want to understand the principal ideal domains, those are the rings for which all finitely generated modules are direct sums of cyclic modules, as long as you're an integral domain. Or they are the rings for which every submodule finitely generated free module is free. And the Noetherian rings, to understand those in terms of their modules, those are the modules for which all of the submodules of the finitely generated modules are finitely generated. So these conditions that are defined not in terms of modules, they're defined in terms of properties of ideals, can be understood in this broader context of modules. And there is a significant power in being able to do this. There's a fundamental theorem of Auslander, Buchsbaum, and Serre that fits in this idea that it was a conjecture for a long time that a certain collection of rings were nice. The niceness condition was defined in terms of ideals. No one has been able to prove it in terms of the ideal definition, that one proves it in terms of this very different condition on the class of all the modules. And to reiterate these points, that these are like the CELO theorems, but for rings, instead of understanding a group by understanding the sets that it acts on, we're understanding a ring by looking at the modules, which are the sets that it acts on. And this is very much like representation theory for rings. And then the points that we saw in red several times, elementary rings have only elementary modules, like the fields, like the principal ideal domains, like the Noetherian rings, and conversely. And the 2 points that we will make in tomorrow's class is that, so in general, modules are not nice. Modules are messy. They're mischievous little creatures. And they're not anywhere nearly as nice as being direct sums of cyclic modules, because that explicitly characterizes the principal ideal domains. And so what do they look like? How can I understand them? And we will see what other niceness conditions, some of the niceness conditions that one can see by using these modules. And so I think what I will do now, before I show you the homework problems, is let me look at this property that I mentioned previously that says that if R is Noetherian, and I is an ideal of R, then R mod I is Noetherian as well. And the way we will prove that is to use a particularly nice characterization of the ideals inside the quotient R mod I. So what do we need to show? That every ideal of R mod I is finitely generated. And the structure theorem that I mentioned just a second ago, the key is that the ideals of R mod I are all of the form J mod I J is an ideal of R such that I is contained in J. And to be very clear, the ideal J is not esoteric at all. It's just the inverse image. So if I take the map tau going from R to R mod I, the one that I always use, then the ideal J is just tau inverse of the, I suppose I need a letter, K, where K is my ideal inside of R mod I. Notice that by what we said before, I'm looking at the inverse image of a submodule of the domain of my homomorphism. And so that will be a submodule of the domain of my function. And that means it will be an ideal of my domain R. But by assumption, R is Noetherian. And so I know that it follows that that ideal J is finitely generated. And just like we did in the previous proof where I used inverse images, the fact that tau is surjective or onto tells me that K is of tau inverse of J, which is finitely generated. I don't need to use tau here. I can just use the fact that K has to be of the form J mod I. And we can use the fact that J is finitely generated implies that the quotient is finitely generated. And so we've shown that every ideal inside the quotient is finitely generated, which is exactly what it means for R mod I to be Noetherian. Right. So last up are the homework exercises. Let's talk about those. Hello?
Yes, excuse me. I think there is a comment. I'm not sure if it is a question or just a remark on the chat. If I recall correctly, it is on your section 2.2. So Hesham said like tau of EI are generators. I'm not sure if he's asking something there, if he can just.
Oh, that was in response to a proof that I was going through where I wrote that, yeah, so that was up earlier with, yeah, the tau of the basis vectors were giving us the finite generators for the, yes, thank you.
Okay.
So let me just say a few words about the homework exercises for today. So the first one, so this is called a universal mapping property for free modules. And the way that it's stated is, I'm going to start with a free module F, which has basis B, and I'm going to take another R module M, and I want to build a homomorphism from F to M, just like we did with the models that we were constructing if I want to have a tau that maps from a free module onto my module M. And so this is the more general statement that I said before, that if you give me any module and any set of elements of that target module, then I can define a module homomorphism from F to M such that the basis vector B gets mapped to the designated element of the module M. And as a special case of that, if you give me a finite list of elements inside my module, say that there are n of them, then I can construct a well-defined, unique R module homomorphism from R to the n to M that sends the ith basis vector to the ith module element in the list. And so the exercise will be to explain what is the rule that one would use for such a homomorphism. Why is that rule give me a well-defined function? Why is it a homomorphism? And then lastly, why does it satisfy this condition, and why is that unique? Now, it may be useful to do part 2 of this exercise first in order to get a feeling for how the arbitrary basis case would look. So this is the case where I'm looking at a finite basis instead of a basis that could be infinite. It could be uncountable, for instance. And then the last exercise, so I talked about these Noetherian rings. I claim that that is a niceness condition. So that means that there should be some rings that don't satisfy that condition, and there are. So here is an example of a ring that is not Noetherian. It is the polynomial ring in infinitely many variables over a field K. One can think of that, if one's not too worried about the technical details, as the union of the polynomial rings in 1 variable, 2 variable, 3 variables, and so on. And in that ring now, there are infinitely many variables, and I can look at the ideal that's generated by that infinite list. That is the set of all finite linear combinations of those vectors that have coefficients coming from the ring R. And I claim that that is not finitely generated. And it's given in terms of an infinite generating sequence. So I can see that it is infinitely generated, but one has to show that, in fact, there's no finite generating sequence. And once one does that, then one has the existence of an ideal that's not finitely generated. And so this is an example of a ring that is not Noetherian. I see that there's a question in the chat that may have been answered. I studied Noetherian rings in terms of the
excuse
ACC.
me. I could read the question for you. Sorry. I suggest that we could answer these questions right before the break. I think we have a few minutes left. And
Yes.
so, the question from Edgar is, he studied Noetherian rings in terms of the ascending chain condition, but they were defined right now without that condition. So why it's necessary to understand Noetherian rings in terms of ACC?
Right. That's a great question. So as Osama pointed out, those conditions are equivalent. There are actually several equivalent definitions for Noetherian rings. So the ring is Noetherian if and only if, and I'm stating what Edgar and Osama have already said for the other people in the audience, that is equivalent to R satisfies what's called ACC, which is the ascending chain condition, for ideals. And what that means is that if you give me, so for every ascending chain of ideals, that the chain stabilizes. So there exists a number n greater than or equal to 1, such that in equals in plus 1, in plus 2, and so on. So the slogan is every ascending chain of ideals or stabilizes. The third condition is the maximum principal for ideals. That is that every non-empty set of ideals of R contains an element, a maximal element, or an element that is maximal with respect to containment. And before I get to the answer for Edgar's question of why is it necessary to understand Ethereum rings in terms of the ACC, let me tie this together to the ideas, the module ideas that I was talking about before. So these conditions are equivalent to saying that every finitely generated module, R module, is, let's say, satisfies ACC on submodules. That is, every ascending chain of submodules must stabilize, and the corresponding condition, every submodule of every finitely generated R module is finitely generated. And every finitely generated module satisfies the maximum principal for submodules. Right, so another instance of niceness condition for the ring that's defined in terms of ideals being expressed and obtainable in terms of niceness conditions for the modulus. Right, so this fits very much with the theme that I was talking about before. Now for Edgar's question. So why do we care about the ascending chain condition? And the answer is that when you have these equivalent characterizations of the Noetherian property, you can use them. I like to say that you play them against one another. So for instance, in the proof of the Hilbert basis theorem, right? So I assume that R is Noetherian. And I want to show R bracket X is Noetherian. And I'll just do that by definition. So I want to show, so we're going to take an arbitrary ideal. And I want to show that that ideal is finitely generated. Now, what I have to do is I have to transform this ideal, which consists entirely of polynomials, somehow into information inside of R, so I can use the fact that all of the ideals in R are finitely generated. And this is the very technical part of the proof, and I see that I'm out of time, so let me give 1 minute of how the ACC comes up. So one uses this to build a sequence I0, I1, I2, and so on of ideals inside of R. And then you get 2 pieces of information about that ascending chain. So R being Noetherian implies that this chain stabilizes. And it implies that each of the ideals I sub j is finitely generated. So it's you would like to be able to just get away with the knowledge that all of the ij's are finitely generated, but it's absolutely crucial that you know that there are only finitely many possible distinct ideals in that list. If you don't know that, then the proof doesn't work, right? And so you simultaneously use the finite generation condition over R with the ACC condition over R in order to verify the finite generation condition in the polynomial ring. So that's one particular instance where you want to think in terms of finitely generated ideals, but you really have to also think in terms of the ascending chain condition. And maybe I'll stop there for our break.
All right. So yes, it's perfect timing for our 15-minute break. Once again, you are invited to stay connected to this conference, and we will continue with the discussion afterwards. Thank you, everyone.
That's right, Edgar. The moral of the story is that ACC is somewhat unavoidable. I would like to think about it as a nice tool, right? It just happens to be a tool with slightly different uses from the finite generation condition. and that if you are flexible enough to be able to use both tools, then you can solve more problems than other people might be able to. But yeah. Okay. And I'll also take a minute for a break. I'll see you all in a few minutes.
Hello, everyone. I think we are ready to resume our discussion. So if you would like, Professor Sutter, you can go ahead.
Terrific. Thank you. First, let me see if there are any questions.
It seems the last remark was routine, no? The link to the course materials, and one more time, an invitation to everyone to ask questions in whatever language they prefer, and we are gonna try to help if necessary.
Wonderful. Well, as we discuss things, if any questions come up, please let me know. Should we think about some of the exercises? Does anybody have a thought about any of these that they'd like to share?
I have an idea for exercise too, but
Terrific.
I'm not sure if I am correct. Well, the first thing is define an homomorphism, phi sub m. Its domain is k of x1, x2 to well, and so on.
Or all the variables or just some
all the variables, yeah.
Okay.
All the variables. To k of, in this case is the first m variables are omitted. I say is k of xm. Well, yeah, the first variable should be xm, and then xm plus 1, and so on. Yeah, and
Very good.
it's defined by phi m of k is equal to k for all k in k. And for variables, phi m of xi, yeah, and for variables, phi m of xi is equal to itself, yeah.
This is a fantastic idea.
And now, well, it's not mine. It's from a professor of mine. I saw it in a class. So, and then suppose that this ideal is Fg. Let's say it's generated by F1 to Fn. Yeah. Then we're gonna take an m, so that for I greater than m, well, greater or equal than m, no xi appears in the f, well, in the f1 to fn. Yeah. And then, yeah, and I is generated by F1 and Fn. Well, we take the variable xm and we write it as a finite linear combination of the Fi's. Yeah, and then we apply this homomorphism, phi sub m. And yeah, and well, by definition, this is xm, but because of the linear combination, it is 0. Yeah, because phi m of fi, because of how we take, how we took the m, this is 0, so xm 0, and that's a contradiction. So it can be a finite generated idea.
That's exactly right. Very nice. A couple of important points to make here is that so notice that I like about your proof, you did not assume that the F's that you chose come from the list of variables, right? And that's, in some sense, that's important. It can be gotten around, but what's important is to show that no matter what finite list you choose, you can never obtain a generating sequence for this ideal, right? And so that's what you did. You took an arbitrary finite list and showed that it doesn't work. And the crucial point is that we are working in polynomials, right? So for any fixed polynomial, it can only use finitely many variables, right? Because of the union condition. Every element has to come from one of the finite polynomial rings. And so the process of taking the finite list of variables that's needed for the finite number of elements, and then essentially throwing all of those variables away. There is one key subtlety in here that's worth noting, is that the FIs are not just in the ring R, but it's important that the FIs are inside of the ideal I, which means they have no constant term. Because that is how you get the zeroness here, because in principle, if the FIs had a constant term, then phi m of Fi would be equal to the constant term, right? So that's used the fact that the FIs come from the ideal I. Very nice. Any questions about that, or any other ways of thinking about it? Very good.
I have well, it's similar. If we take F1 Fn in the polynomial ring that have all the variables that express F1 as Fn, no?
How to Brandon, I'm sorry I lost you there.
Sí, yo.
So express the F1 as how?
It's a polynomial and it's expressed like a sum of n variables, no? X I1 hasta X mi.
Very good.
We can do for all f I, no?
Yes.
And f1 of fn belongs to the rank of polynomial x1. El supremo, será el supremo.
So you are doing pretty much the same initial step here, right? So you're saying each one of these uses a finite list of variables. And maybe what I'll do is say that means that they use some finite list. Go ahead.
Bueno. This belongs all f1 as fn belongs to the ring the x1 as the xt with t very much big. No sé cómo decirlo. So,
yes, absolutely correct.
And the ideal x1, x2, x2, bueno, for all naturals.
Yes.
Don't belong to ring the x1 as the xt.
Sorry, could you say again which one does not belong there?
The ideal I.
Like this?
Mm-hmm.
Perfect. Okay. Is that so? That is close to bringing a contradiction and using the same idea. I mean, as you already pointed out, similar. You want to use the fact that the finite list of polynomials only uses a finite number of variables. The ideal I uses infinitely many variables, but one has to be careful because just because these polynomials live in a small polynomial ring, that when you take the ideal generated by those inside of the large polynomial ring, it will not be contained in the small polynomial ring. Because in the linear combinations that I take for elements in here, the GIs will come from the larger polynomial ring. Right, so even though the generators here come from the smaller polynomial ring, when I take the ideal they generate in the larger polynomial ring, it will have elements that are not in the smaller polynomial ring. And so this is what the other argument was doing. Was I wasn't sure if the previous argument was going to try and do this, but they avoided it, was to use this homomorphism. And one does have to check that this is a well-defined ring homomorphism, but it is, in order to force that finiteness of that number of variables in order to give us a contradiction. But the idea is definitely on the right track. Yeah, and I mean, maybe yeah, I think that there is probably an argument along this line that doesn't use homomorphisms. So for instance, just like we were talking about before, if I have x t plus 1, I can write that as some linear combination of fi's, which this one only uses the variables x1 up to xt, but the problem is that the GIs might use higher variables, for instance, right? And so one has to figure out a careful way in order to draw a contradiction from the fact that there are elements. One has to use the fact that this is a variable. Yeah, and there's probably, maybe there's a degree argument that one can use for that.
Professor, I believe the last remark was a request to repeat one of these arguments. I believe Edgar means the first argument, not the one on the screen, but the one with the homomorphism. I think so. Yes. Thank you.
Okay. Absolutely. Let me give myself a little bit more room here. So, Edgar, stop me if there's a point where we should clarify things. So the idea was that we're going to construct, so for each positive integer m, we're going to construct a ring homomorphism from the original ring with all of the infinitely many variables, and it has its codomain to be still an infinite polynomial ring, but not starting necessarily at x1, but starting at xm. And the way that this homomorphism is defined is by having it be the constant function on the constants. It's also the constant function on the variables that are indexed in the range greater than or equal to m. But then for the variables that live in the domain that do not live in the codomain, we have their images to be 0 in the codomain. And one checks that this is a well-defined ring homomorphism by defining, so let me see here, so phi m of, so if I have some polynomial of, the writing is out. I'm trying to think about some good notation for this. Oh, let me give some examples instead of writing out the general the noting. So once you tell me what the function has to do to the variables and what it has to do to the constants, then if I want it to be a ring homomorphism, it has to respect multiplication. So the elements that look like this, it has to be phi of the first thing, which gets left alone, and then multiply by phi of the second thing, down the line until you multiply by phi of the last thing. And then for finite sums of terms that look like this, it has to also respect addition, and so you would just break it up across the sum. And now the idea is that if the ideal I were finitely generated, then it would have to be generated by a finite list of polynomials. Because each one is a polynomial, each one only uses finitely many variables. And so the total list of variables used for this finite list of polynomials is a finite list. And so that can be summarized by saying that there exists an integer m such that each of the fi's is in this smaller polynomial ring. And now what we're going to do is we're going to look at what happens with the variable xm, which is by definition in the ideal I. Now, because it's in the ideal I, that means that I can write it as a linear combination of the generators, which we do here, where the coefficients in the linear combination come from the ring R itself. And then when we apply, oh, there's definitely, so let's see if anybody can spot, there is one error in what I've written. The idea is correct, but there's a minor typo that the xm, so that is by definition of phi m is equal to phi m of xm, but phi m of xm is phi m of this sum. And so I can put that sum into the map phi. Let me write out an extra step here. So this is phi m of summation over I, gi fi. And now because phi m is a ring homomorphism, it respects the finite sum. So this is sum I phi m gi fi, and it also respects multiplication. So okay, I got it. Good. Right, and the typo, let's catch this while we're here, is that there should be a phi m here in front of the gi. Apologies for that. Good. We don't know what the image of the gi is, right? That is absolutely correct. The gi's almost certainly in this, hypothetical contradiction situation will use other variables. But notice that I don't, so I wrote gi there, but it should have been phi m of gi. That's absolutely correct. I see that there is a question in the chat about an equivalence to DCC in finitely generated. That is a fantastic question. And the answer is yes, but it is too complicated to fit in the margin of this particular book. There is, so in the world of the descending chain condition, and then we'll go back and look at the other exercises. In the descending chain condition for ideals, that is satisfied if every, what's the best way to, so one has to be careful because the Artinian condition implies the Noetherian condition. But the converse fails in general. And so that says that DCC for ideals does imply that all ideals for that ring are finitely generated. But the condition, there is a, right, so you have every ideal is finitely generated. That one you get for free. You have the minimum principle instead of the maximum principle, the descending chain condition instead of the ascending chain condition. There is another idea that's the dual of finitely generated ideals, and it says that every cyclic module is finitely embeddable. And so, right, so ascending chain condition has all the containments going this way. The descending chain condition reverses those, and that corresponds to turning the surjections that we use for our finitely generated modules into injections for what are called injective modules. And the question is whether or not your modules can be embedded inside of injective modules that are nicely finite in a sense. So that's the corresponding version. The problem is that it requires some very technical notions in order to state it correctly and rigorously. And so I don't have time to do those right in here.
Well, I am sorry to interrupt, Professor. Well, this is like a question from myself. I myself was feeling a bit curious about this relationship between Noetherian and Artinian rings. And maybe could you share with us a reference for the kind of property you described in your last sentence? Because at least for me, this was completely unknown.
I want to say that there's probably a better reference for this, but one can find it in the textbook of Enoch's Agenda. That's called Relative Homological Algebra. If I remember, I will try and find, I'm looking over on my shelf to see, let me look and see if I have a copy of that at home today. Hold on. It's been 7 or 8 months since I've been in my office, and that's where most of my books are. Let's see here. Is it in finitely embedded, page 90. is where they talk about that. And let me see if the statement that I was claiming to be true is actually true about Artinian rings. Yeah, it's true, but they're not stating it in here that I can see. Let me see if I can find a reference for that. The idea is that in general, the injective modules are harder to describe than the free modules and the projective modules. And so one has to talk about, so one has to do a little bit of work in order to be able to say what, and it's, I guess I've used the term wrong, it's finitely embedded. So that's correct. And I believe that it's, it's equivalent to every finitely generated module being finitely embedded. And so the idea is, instead of finitely many copies of R that are surjecting onto your module, that the dual version of that is that your module M embeds into finitely many copies of, this has lots of different words, but the injective cogenerator. Yeah.
Okay, so sorry, one more detail. Excuse me if I'm wrong, but for example, in the case of abelian groups, this E, the injective cogenerator, I believe it's Q over Z. Am I mistaken?
That's correct. And of course, the ring of integers is not Artinian, and so you're not going to have your finitely generated modules sitting inside of finitely many copies of that. And in fact, if you have any integral, I don't want to make too bold of a statement. The idea is that in the Artinian case, not only are all the ideals finitely generated, but all the prime ideals are maximal, and there are only finitely many of them. And so the injective cogenerator in this case is the direct sum of the injective holes of the corresponding residue fields. And now, in general, these are all Artinian modules. And so if you have a module that sits inside of a finite direct sum of this module, then it has to be Artinian. And then on the other hand, yeah, I want to think about the converse, about why the cyclic modules being finitely embedded would imply the ring is Artinian. Yeah, but this is the basic idea. And in this situation, right, your Q mod Z, there are infinitely many maximal ideals for this ring. And so this one decomposes as a direct sum of infinitely many p-torsion pieces. And so there's definitely some difference here. So to answer the question in the chat, finitely embedded means exactly this condition, that your module M, there's a one-to-one homomorphism into a finite direct sum of copies of the injective cogenerator, which is something that we haven't defined, but in some examples, the injective cogenerator over Z looks like that, and the injective cogenerator in the Artinian ring case looks like that. You're welcome.
Yeah, thank you very much.
Yeah, you're welcome. The reason it doesn't come up very frequently is because it's somewhat technical, getting into these details. But yeah. Any other questions? Oscar asks if Rx is Noetherian, then R is Noetherian, right? The answer to that is yes. Oscar, do you know the proof? So there's a technically it looks much stronger than Hilbert's original result, but so Hilbert's original Hilbert basis theorem was this implication. Oscar is asking about the converse to that, and I'm giving a little bit of a flourish here to point out that there are actually several strengthenings of that. So the proof of it is actually incredibly short, and it uses a piece of technology that we've already stated. So the key idea is that R as a ring is isomorphic to the polynomial ring modulo the ideal generated by the variable. And so if we assume that this ring is Noetherian, then by a property that property 3 that I proved at the end of the lecture, that every quotient of that Noetherian ring has to be Noetherian, but that this particular quotient is isomorphic to the original ring R. And this isomorphism, just while we're on the topic, remember on class yesterday, I talked about the fact that if you want to show that something is isomorphic to a quotient, then the first isomorphism theorem is the way to go. And so that's how you prove this isomorphism. R bracket X maps to R, exactly similar to the homomorphism we had earlier, call it phi, and it says phi k equals 0, or sorry, equals k for all k in R, and phi of x equals 0. And so what this homomorphism does is it just plucks out a constant term of the polynomial. And one can check that this is a surjective ring homomorphism with kernel of phi equal to the ideal generated by X. And so the first isomorphism theorem, and you'll excuse me if I do that for here on the side. First isomorphism theorem says that the target is isomorphic to the domain mod the kernel. And so that's exactly R bracket X mod X. And so the straightforward example that we did shows that if this ring is Noetherian, every quotient of it is Noetherian, and so this ring has to be Noetherian. And you can see the same proof works if you have that this ring is Noetherian for some n, maybe you don't know what it is, because you would just substitute in here the list of variables that you started with, and you get the same isomorphism here by taking the list of variables. Each of the variables goes to 0, and what that does is if you have a multivariable polynomial, then it just plucks out the constant term, and it has the same property just being generated by the original list of variables. Very clean, very neat. Any other questions? Aha. Oscar has a lot of questions. This is great. If R is Artinian, then is R of X Artinian? Never, in fact. And the proof for that uses a tiny piece of technology. Let's see here. Beep, bop, beep, doop. So we'll state the even stronger theorem that as long as R is not 0, then R bracket X is never Artinian. And the reason is Artinian rings have only finitely many maximal ideals. But okay, so I'm doing about I'm not doing the smartest proof, so I'll do this proof and then I'll do a smarter one. R bracket X, one can show, always has an infinite number of distinct maximal ideals. Now that's easy if R itself is infinite, but if R is finite, one has to do a little bit more work. But now I'll give the simpler proof. There is an infinite descending chain of ideals that never stabilizes. And the fact that it never stabilizes is where you use the fact that I've got a non-zero ring. Right? If you have the 0 ring, then these are all the 0 ideals and everything's pretty silly. So there's a descending chain that never stabilizes. Yeah, and that also gives an example of some nice rings. So we said that Artinian implies Noetherian, but the converse fails. And you can see that using the Hilbert basis theorem. So that ring will be Noetherian by the Hilbert basis theorem, but by the argument we just gave, it's not Artinian. You're welcome. Other questions?
So there is another, question. Edgar is asking if you would like Professor Sutter to share this manuscript, the ones that you are doing right now. I don't know how to call them, but that you're doing by hand.
Ah, these notes.
Yeah.
Yes, I will try and do that. Yeah, that's a good question. Thank you for asking that. Write myself a note. The trick is to see if I can export them as a PDF or not. But I should be able to do that. If nothing, I can just take screenshots and share those. Good. Good question. Thank you for asking that. I'll go through and also look at the notes from last time, the handwritten parts, and share those also. And those will be on the notes page sometime, either today or tomorrow.
Excellent. Thanks.
You're welcome.
So just let me translate this. I just want to make sure to answer. Ah, okay, so Edgar is clear about your answer. Okay, great. Thank you.
Perfect. Did anybody get a chance to think about the first exercise? Either the finite version or the infinite version? So if I have a free module with a basis B, I want to define a homomorphism out of the free module. Actually, let's talk about the finite case. So free module with basis given by the EIs. How do I define a map out of that free module? Somewhere I have to use the fact that my R to the N is a free module, or something about the EIs. Any suggestions?
That could be B can be written as a linear combination of the bases, right? So we could send this linear combination to the sum Yeah, well, phi of B is the sum of Ri's MI, right?
It's absolutely correct. And the reason why that is the correct, right? So remember there's a claim that this is a unique homomorphism. So it looks like we made some choices here, but we really didn't. And the reason is that if you have any map that works, then phi of V has to equal phi of some I Ri EI, which has to equal some I phi of Ri EI, because the homomorphism, module homomorphisms respect sums, and it also has to respect scalar multiplication. But now, by assumption, I'm going to declare that. Right. And so the idea here is that if you want a particular set of properties, so modular homomorphism with these conditions, that forces all of the rest of the decisions that you have, because we used both of the axioms for a modular homomorphism along with the assumption of what do I want phi to do to each of the basis vectors. And Brandon is exactly correct that in order to show the uniqueness, what we would do is so first we have to show that this definition is actually a well-defined R-module homomorphism. And well-definedness is exactly where we use the span and linear independence conditions for the basis, is that because every element of V of Rn can be written this way, right? That's the span condition. And then the linear independence condition says that this representation of V is unique, right? And so even though it looks like there are some choices, this representation is unique. And that's what gives us the well-definedness. And then one goes through and the R-module homomorphism conditions are fairly straightforward. So if I take a phi of V plus W, that's equal to phi of some I Ri EI plus some I Si EI, say, and then I combine those together. And I apply the rule. Right? And then once we know that it's a homomorphism, as Brandon said, then we would use this argument to show. So if you suppose that psi is another homomorphism, then we would say that psi of V is psi of this thing, respects the sums, respects the scalars, and then that is equal to phi of some I Ri EI which is phi of v. So if you had a different one, then it would have to give the same output as the one that was just given, and so they would have to be equal. That's exactly right. And one does something very similar using almost exactly the same proof over here. So phi of v in this case, where I have a basis capital B, so my v can be written as a finite sum coefficients times basis vectors, and then we write phi of that thing is phi of sum B and B, finite sum RBB has to equal to the sum B and B, finite RB MB, right? So in the finite version, if you tell me where to send the basis vectors, then you've told me what to do to the linear combination. And the same thing is true over here. If you tell me what to do with each basis vector, then you've told me what to do for the linear combination. So the proof of the infinite case is actually almost identical to the proof of the finite case. So you can argue two different ways. Prove the finite case first so that you can see how to prove the infinite case, or you can derive the finite case as a corollary to the infinite case. I find the finite case a little bit more manageable to wrap my head around the first time when I'm thinking about it. And I think maybe we have one more minute for a question if anybody has one.
Yes, I think Brando is giving a suggestion. So he says
Right.
if there exists another homomorphism.
Right, and that's what I was doing over here in response to what Brandon was saying, is that in the uniqueness case, I would assume that psi is another homomorphism that satisfies these conditions, and then I prove that psi has to equal phi. That's exactly correct.
Okay, so sorry, my mistake.
No, it's just fine. I should have written more details down. All right. Thank you all very much. Oh, thank you, Ed. I appreciate that. I'm looking forward to telling you tomorrow about the introductions of homological algebra. Okay,
so the time is up, and again, thank you to Professor Sader for this beautiful explanation of this subject, and we'll see you tomorrow.
Perfect.
Okay.
Thanks,
bye.
everybody.
Thanks. See you tomorrow.
Wonderful. Oh, that is a good question. I generally don't think about non-commutative rings, so I don't know the answer to that question. I suppose you have to be careful if you mean commutative polynomial ring or non-commutative polynomial. Is your variable, I don't know. That's a good question. You're welcome. All right, everyone. Thank you very much. See you tomorrow.